Hello and welcome to another lecture on applications of the integrals. So far we have discussed about the area of bounded regions. Today we shall be discussing about the problems based on finding the area under the given ellipse and the problems based on finding the area under the given circle. First we shall be discussing about the problem based on finding the area under the given ellipse. For this we consider a problem which says that find the area of the region bounded by the ellipse whose equation is given as x square divided by a square plus y square by b square is equal to 1. Now here, since the equation of the curve, which is x square by a square plus y square by b square equal to 1, since all powers of x and y are even in the given equation of the curve, so we can make out that it is symmetrical about both the axes and we can have the figure of the ellipse as shown. And therefore area enclosed by this ellipse is equal to 4 times the area enclosed by the ellipse and the coordinate axis in the first quadrant. Here we slice the area in the first quadrant into vertical strip as shown. Here we observe that each vertical strip has its lower end on the x-axis and its upper end touches the ellipse. So the approximating rectangle is shown in this figure has width of delta x and its length is equal to, let's say, y. Area is equal to y delta x, and this approximating rectangle can move from 0 to a. So the required area is equal to 4 times the integral of y dx with limits 0 to a. Now here, since point P with coordinates x and y lies on this ellipse whose equation is x square by a square plus y square by b square equal to 1. Therefore, y is equal to b by a root of a square minus x square. Therefore, area is equal to 4 times the integral of y, which is equal to b by a root of a square minus x square dx with the limit 0 to a. This is equal to 4b by a into integral of root of a square minus x square with respect to x with limit 0 to a. This is equal to 4b by a into the integral value of this expression, which is equal to 1 by 2 x root of a square minus x square plus 1 by 2 a square sine inverse x by a with the limit 0 to a. Now we are going to substitute x with the values of a and 0, and thus we have this equal to 4b by a into bracket 0 plus 1 by 2 a square sine inverse of 1, which is equal to 4b by a into 1 by 2 a square pi by 2, since sine inverse of 1 is equal to pi by 2, which is equal to pi a b. Thus the area is equal to pi a b square units of the given ellipse. whose equation is x square by a square plus y square by b square equal to 1. Next we are going to discuss the problems based on finding the area under the given circle. Here we have to find the area of the region which is specified as x square plus y square is less than equal to 1 and x plus y is greater than equal to 1. Now here let R is equal to the given region. Thus R is equal to the intersection of two regions which are x square plus y square less than equal to 1 and x plus y greater than equal to 1, which is equal to intersection of R1 and R2, where R1 is equal to the region x square plus y square less than equal to 1 and R2 is equal to the region where x plus y is greater than equal to 1. Clearly x square plus y square equal to 1 represent a circle with origin as its center and radius as 1. Since x square plus y square is less than equal to 1, so region R1 represent the interior of this circle. Next moving to region R2. Now here since x plus y equal to 1 is the equation of a straight line which is as shown, and it cuts the x-axis and the y-axis at points 1, 0 and 0, 1 respectively. This line, that is x plus y equal to 1, divides the xy plane into two parts, one representing x plus y greater than equal to 1 and the other x plus y less than equal to 1. Now since the origin, that is 0, 0, does not satisfy the inequality condition of x plus y greater than equal to 1, therefore region R2 is the region lying above the x plus y line. Hence the region R is the shaded region as shown in this figure. Now if we slice the shaded region into vertical strip as shown, we observe that each parallel strip has its lower end touching the line x plus y equal to 1 and the upper end touching the circle which has its equation as x square plus y square equal to 1. So approximating rectangle is as shown and its length is y2 minus y1 and its width is given as delta x, and therefore area of this approximating rectangle is equal to y2 minus y1 into delta x. Now since the approximating rectangle can move from x equal to 0 to 1, so we have the required area equal to integral with limit 0 to 1 y2 minus y1 dx. Now since point P, which lies here, has the coordinates x, y1 and point Q lying here has the coordinates x, y2. Now as we can make it evident that point P and Q lie on the line which has its equation as x plus y equal to 1, and point Q lies on the circle with equation x square plus y square equal to 1. Therefore x plus y1 is equal to 1a and x square plus y square y2 square is equal to 1. So we have y1 equal to 1 minus x and y2 equal to root of 1 minus x square. Now substituting these values of y1 and y2 in equation number 1, we have the area equal to integral of root of 1 minus x square minus 1 minus x dx with limits 0 to 1, which is equal to 1 by 2 x root of 1 minus x square plus 1 by 2 sine inverse x by 1 minus x plus x square by 2 with limits 1 to 0. This is equal to 0 plus 1 by 2 sine inverse of 1 minus 1 plus 1 by 2. This on simplifying is equal to pi by 4 minus 1 by 2. Thus the required area is equal to pi by 4 minus 1 by 2 square units. With this we conclude this lecture on applications of integrals, which was based on the problems of determining the area of an ellipse and a circle.